Que la que hay, mi gente? Welcome to eCruz Learning, where it's just that easy. With your favorite host, Master Cruz. And today we're going to talk about how to use graphs and how to read them. So here we go. We're going to talk about a fish that it's called growth of a largemouth bass. So this is the largemouth bass. As you can see, it has a large mouth. And here is the growth. Every year, it grows a certain amount of inches. So we have data that after 1 year, the length will be 6.5 inches. After 2 years, it will be 11 inches. After 3 years, it will be 14 inches, so on and so forth. So the first thing that we could do is create a graph to plot this information so that we could see a little bit better what the pattern of this data is. So on the right-hand side, you can see that we created a graph with the name of the table, growth of a largemouth bass or bass, I should say. But the age is the x-axis, like it was on the x side of the table, and the length is the y-axis, and you can clearly see the units in parentheses. These are years and these are inches. So if we take a look at the beginning, obviously, when 0 years have passed, it has not been born yet, so it starts at 0, 0. And then after 1 year, like we mentioned earlier, it will measure 6.5 inches. After 2 years, it will measure 11 inches. So I hope that you can see that I always go to the x-axis. And given the value of the x-axis, then I find the y-axis. So if I wanted to read this graph, I will say that after 3 years, the largemouth bass has grown 14 inches long. Okay, and this is how you will read every single one of them. Now, if we want to talk about what is happening, how can we model the situation? Well, what we could say is that as the years increases, so the older the largemouth bass gets, the longer it gets, okay? And it looks like in the first years, it's growing at a faster rate, and then it just keeps growing at a slower rate. So on year 4, it looks like it was 16 inches, but in year 5, it only grew up to 17 inches. So it only grew up 1 inch versus the first year that it grew 6.5. And after the second year, it grew, well, 1, 2, 3, about 4.5 inches. So as it gets older, it gets longer, but it grows at a slower rate. So that's what we have to look at so that we can start learning how to read tables and graphs. Okay, so over here we have another example, example 1, that talks about the year and the stamp cost of cents. So, you know, the stamp that we put in the letters, this that only used to cost 6 cents and then 2 cents. It's crazy. All right, as the years progress, it becomes more and more expensive. And we have data up to 2010 where it only cost 44 cents. And I say only because it's cheap compared to today, but as you can see in 1885, it only cost 2 cents, which is crazy. Well, if we take this information and you can see that it was 6, 2, 3, and this is going up, but there's a jump here of 20 years, a jump of 5 years, a jump of 30 years. So when you come over here and you see the data, this is the same data on the table, but now it's plotted in a graph where the x-axis is the year, x is usually the time, and then the stamp cost is the y value. And you can see that somewhere around the 1960s, maybe, it began to grow rapidly. So it was constant for a long period of time, and then it started to grow faster. So that's the difference between the rate, and that's how you can see the different graphs, and you can read them. It looks like this is an exponential growth, right? It was slow, 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 and then it just boom, it exploded real quick. So let's look at the last example. Well, actually, let's look at example 2 real quick so that we can understand a little bit of what's going on. And this example is actually really, really good because this has to deal with skydiving. So use a distant time graph to answer the following questions. So here is the graph, and like I said, time is always in the x-axis because it's always independent, and y is the distance in feet. But is the distance fallen? So this is not the altitude from the ground. This is you're all the way on the top, and how many feet have you fall after you jump from the plane. So this says, how far has the skydiver fallen after 10 seconds? Well, the way I find that is that I go, they want how far, right? First, I have to figure out what do they want. They want how far, and how far sounds like distance. So they want a y value. If they want a y value, they have to give me the x value, and the x value is 10 seconds. So on the x-axis, I'm going to find 10 seconds, and I'm going to go up until I find wherever this line crosses, or where is 10, right? So 10 is somewhere around here. That means that the answer will be somewhere around here. So if we scroll down, we're going to be able to see that at 10 seconds, this is somewhere about 1,300 feet or 1,300 feet. And that's exactly what the answer is. Okay, so here we go. How long does it take the skydiver to fall 2,000 feet? So now, how long does it take? Sounds like they're asking for time. And if they ask for one variable, they have to give us the other. So they gave us the 2,000. So then we go here and 2,000 the distance fallen. And then I'm going to follow this until I find my graph. And the graph is right here in the red. And the question is, what is the y value? Well, if I'm at 2,000 and I'm here, it looks like the x value corresponding to that is somewhere around 14 seconds. So it takes about 14 seconds to fall 2,000 feet. Now, the last question says, describe the fall of the skydiver in the first 5 seconds, then next 15 seconds, and then final 10 seconds illustrated. So when we look at this graph, it looks like there's 3 different types of slopes, right? From 0 to 5 seconds, something happens. It looks like the diver falls greater distance each second for the first 5 seconds. And we know that because it's increasing, okay? And then look what happens here. It is also increasing, so that says he then falls about the same number of feet each second for the next 15 seconds. And the reason for that is this is a straight line. Because it is a straight line, that means the rate of change is constant, is the same. And then he then falls at a much slower constant rate during the last 10 seconds. So instead of falling very quickly like he was falling here, now he's still falling, but he's falling very, very, very slow in the last 30 seconds. Probably what that means is that they open their parachute and they're ready to land on the ground. So that's how you would describe the altitude. How about if we describe the speed of that skydiver? What is going on with this speed? Well, it looks like at the beginning, the speed he was accelerating, right? It was moving faster and faster every time. And that's why here, the first 5 seconds, the speed was dramatically increasing. Now over here, because he was falling at a steady pace, linear, completely linear, that means that he was moving, but he was not speeding up. He was going down at the same amount of speed. And then when the parachute opens in the last 10 seconds, there is a dramatic drop on the speed. And then he's still falling, but he's falling at a very, very slow rate. So that's what that means. The last example, now let's do the last example, which is example 3. Very, very simple example. I'm just gonna go over it real quick, and then you can jump into doing your practice problems and coming up with some interesting stories. So here we have somebody who's hiking a mountain. So some mountain hiking, and it says that Wadsworth spent a day hiking in the mountains, and Mrs. Wadsworth GPS enabled sports watch record her heart rate and position, including altitude. So we're going to talk about Let's see what's going on. Now we don't see that. We don't see it anymore. Let's see what's going on. Hold on. There you go. There you go. So here we go. So we can track two things. We could track the height and we could track the heart rate. So on the graph below that it talks about altitude, right? It talks about altitude. Let's see if this fixes itself. What's going on? Here we go. So this is literally the shape of the mountain, right? It looks like she went up and then she stayed steady. She was flat for a few minutes, for a long time, for a few minutes. Then she went down the mountain. Then she went up on a steeper slope. Then she stayed up for a long time, and then she came back down. So for some time, as she is climbing the altitude and gets to the highest part, well, it looks like her heart rate goes up and it stays up, right? Her heart rate is elevated as they ascend the first slope. So here's the first slope. Part B, it looks like her heart rate returns to normal while they are at the top of the mountain. So it looks like they stop, they're gonna watch something, up there, look around, take some pictures. Then they're gonna go down in altitude. So they're gonna go down the slope of the mountain. But it looks like when they go down, their heart rate is elevated slightly as they walk hard down the mountain. Okay, so here it is, elevates a little bit, and it stays a little bit steady but elevated. And then when they go down, they go even higher. When they start climbing a steeper slope, her heart rate is way high. It's elevated greatly as they climb a steeper slope. Then again, they reach the top of the mountain, of the second mountain, and her heart rate returns to normal. And then as she descends the trail, right, her heart rate remains slightly elevated, but it's not as bad as when you're climbing. So this is how you will read a graph. I hope that this helps. If you need additional help understanding graphs and how to talk about X and then about Y, like as time passes, the heart rate gets elevated. As time passes, the altitude gets elevated, or it stays the same, or as time passes, the altitude goes down. That's how you read those things. If you need additional help, please visit us at virtualmathmasters.com so that you can schedule your free tutoring session. This was Master Cruz with Icarus Learning, and it's just that easy.